good afternoon, everyone. No, it's still good morning. Got some stuff here. I don't really, you could frantically try and copy it. I probably wouldn't. You can always go back and look at this video and write it down some other time. Essentially what I've got here are most, if not all, I might have missed one, but not many, of the antiderivatives that you're going to be looking at. They have other names. They're called the standard integrals. There's the power rule, add 1 to the power, divide by new power. Here's one I don't think we've touched on. If we have, it's very rare. But if you want to do something like 4 to the x or 5 to the x, as long as it's not e to the x, then its antiderivative is a to the x, but you then divide it by the natural log of a. So that makes it a little bit different. Okay. 1 over x is the natural log of x. The reason I've got this written down at the side is that sometimes it is and sometimes it's not there. When you deal with logs, you really can only use values of x that are positive. So if you were going to, do an integral with 1 over x, you might occasionally see that. And of course, now that I see that, I forgot the plus c. These ones are pretty standard ones from the trig world. I'm pretty sure we've covered them at least once somewhere. These ones, not so obvious. But can you remember doing the derivative of the inverse tan, the inverse sine, and the inverse cosine? Well, this is the antiderivative of this fraction is the inverse tan, and of these two, the inverse sine and the inverse cosine. They're pretty rare, but you'll see them from time to time. Here's a guy we should be really familiar with, the fundamental theorem of calculus, which basically says if you want to find the area under a curve from a to b of some function f of x, you evaluate the antiderivative at b, and then you take away the antiderivative of a. So what's going to happen today is we're going to get plenty of practice at finding antiderivatives in areas under curves. So let's jump straight into my first question. This one is like question 20, and I believe it's we're still in 5.3. So the integral from 1 to 5 of 2x plus 1 over x. Now, antiderivative of this guy, add 1 to the power, divide by the new power. Antiderivative of 1 over x is the natural log of x. So that's the antiderivative thing. And the way we set out the working is you draw a big vertical line and you put x equals 1 to x equals 5 on it. And then on the next line, you substitute x with a 5. So you get 5 squared plus the natural log of 5. Take away 1 squared plus the natural log of 1. I'm doing this in more lines than you probably would want to, but that's 25 log 5. Take away 1. Take away the natural log of 1. That's 24 plus the natural log of 5. What number is the natural log of 1?
0.
Yeah, so if you're going to add 0, does it matter? No, you just leave it blank. Now, can you imagine a different question where there was a log 5, take away a log 2? So imagine that's kind of where my answer is, right? This is the correct answer for that question. But just to show you the kind of little tricks of the trade that you need, you try and simplify your answer. I call it style points as much as possible. If you have 2 logs subtracted, can't you combine them into a single log of 1 division? Might not seem like a big deal, but you should do it. It's part of the style point rule. Style points are, essentially when there's numbers involved, the style points are make the answer as simple as possible. Right? 2 terms is considered simpler than 3. And that's the end of that one. Now, next fella is the integral from 0, in my case, pi upon 4, of the secant of theta times the tangent of theta d theta. And if you prefer secant x tan x dx. So we need to find the antiderivative of this expression. What is the antiderivative of secant theta tan theta?
Secant theta.
Agreed.
Yeah.
And it's going to be evaluated at theta equals 0 to theta equals pi upon 4. And that's simply just going to be the secant of pi upon 4, take away the secant of 0. And all the calculus is finished now, but not the final answer. That's not the answer I'd want you to write. We want to know what the value of something is. And secant or sine or tangent, any of the trig guys, if you've got an angle, you should try, and most of the time you will be able to find out what it is equal to. But you need to do it as an exact value. If you just plug that into the calculator, yeah, you might get the answer 1.414 and the whole of the decimals. And that's not good. So, as a side issue, here is some Calc 2 stuff that you should know. Since I'm interested in the exact value, I'm keeping away from my calculator because it tends to give decimals. But I do know that a secant is 1 over the cosine of pi upon 4. Are we all comfortable that a secant is 1 over a cosine? Right, that's a 142 thing. Next is standard angles, pi upon 3, pi upon 6, pi upon 4, right? Those guys typically, don't they have in your unit circle exact values? What is the exact value of the cosine of pi upon 4, for instance?
Square root 2 over 2, I think.
Yes. That's fine. Except, do you really, I mean, you might want me to, but you know I'm not going to, right? You're not going to leave a fraction looking like that, right? You're not going to leave it hanging, right? You're going to make it look a little bit better. And so this has actually got more steps than you think, perhaps. 1 over something is a reciprocal. So isn't that the same as 2 over root 2? Are you happy about that? Okay. Now, you might say, hey, I'm good. Nope. Fractions really shouldn't have square roots in the bottom if you can avoid them. And this is from Math 99 now. And in Math 99, can't you, fancy name is, rationalize the denominator? What you do is you multiply the top and bottom by square root of 2. That gets me 2 square root of 2 over 2. Oh, that was nice. The 2's cancel. And there is your answer. Did you see how much work was involved in making that a nice answer? It wasn't just I'll hit the button on my calculator and see what kind of decimal comes out. That's not good. Secant of 0 is going to be much easier because it's going to be 1 over the cosine of 0. Cosine of 0 is 1, so you're just going to get 1. That's the final answer. So you can't just think to yourself, I'll do the algebra part, right? I'll get to there. And it doesn't really kind of matter what I do after that, you know, anything will work. No, it won't. There is just as much work after you've done the algebra, the calculus part, and very often as there is before you get to that. And so that is the end of that fella. See what other ones I can do. This one is like 23. It's integral from 1 to 2. We don't have any techniques for doing fractions that look like that. Right? There's no way in the world we're going to be able to do that the way it is. So we need to figure out how to re-express this so that one of these guys over here, or more than one perhaps, can be used. I'm looking for ideas. What do we do?
Split that bottom V up and deal with each half of the top separately.
I'm assuming that's what you mean, Sabrina? Yeah. Good technique. I would do that. And if you do that, you get 1 over V plus 4 V cubes. The antiderivative of that guy is log V. Add 1 to the power, divide by the new power, you get that. And then I'm just going to do some I do a lot, especially my higher levels. I just do dot, 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 which means can you keep going and get an answer and the thing's fine, right? Now, that was the way my brain works, but there is another way to tackle that same question that is equally correct and also works. Can someone see a different approach to that problem?
Multiply the top by V to the -3 power.
Agreed. Now, for some of you, was that the way your brain was thinking? Right. That's perfect. Don't change your mind. Don't go this way because, you know, somebody else said it. You know, there's more than one way to skin a cat, right? Now, when we distribute it, you get that guy plus 4V cubed. Now, there's a little, and it's only minor, but it is important. So you notice that the V to the -1 gets rewritten as 1 over V. Did you see that? Now, normally, if that was V to the -2 or V to the -3, I would have left it exactly as it was because I could have used the power rule. But you cannot use the power rule in this guy. Remember, this guy goes weird if you add 1 to the power and try and divide by 0. It becomes this guy because doesn't this guy generate a special case, right? 1 over V is the only version of the power rule that isn't a power rule, right? It's the only one you don't use a power rule. So I guess the moral of that story is that there's at least 2 ways to tackle this question. And who knows, somebody might have come up with a third one I can't even think of right now. The only rule about that is as long as it's mathematically correct and you do it right. That's the only rules, right? I don't want you to make a rule that's just luck. Well, when I done it the first time, I got the right answer, so it must be okay. Well, you know, can't you do all sorts of stupid things and they just work? But I wouldn't advise you to, you know, do the rest of your math career using it. No, that was good. I love sci-fi. One of the things me and my wife actually share. There's lots of things she likes to watch that are not my favorite, but we do like science fiction. And in science fiction, there is an old TV series. I think they made a new version of it. So here goes. Danger, Will Robinson. Danger. This integral has got danger in it. It looks pretty innocuous, doesn't it? And I'm going to do, oops, don't need that. I'm going to do the easy bit first. The antiderivative of 5e to the x is 5e to the x. Now be very, very careful. What is the antiderivative of 3x to the power of e?
Would it just be the same power rule because e is just a number? So x to the e plus 1 over e plus 1?
Oh, you have made my day. That is exactly what it should have been. Do you notice that people tend to get confused when there's not numbers there? Another example of that same would be, wouldn't x to the pi, right? X to the power of pi, wouldn't it be done the same way? Right. Now, it does make your answer look really weird, but that's not your fault. If you plug in 1 here, you get 3 over e plus 1, 1 to the power of e plus 1, plus 5e to the power of 1. Take away 3 over e plus 1, 0 to the power of e plus 1. Add 5e to the zeros. Okay. What number is e to the power, what number is 1 to the power of e plus 1?
1.
1. So wouldn't that just be a 3 over e plus 1 guy? Would you agree e to the 1 is just called e, so 5e? What number is 0 to the power of e plus 1? 0 to the power of e plus 1.
0.
Just 0. So wouldn't that whole thing be 0? And isn't e to the 0 1? So that's 5 times 1. So you're going to take away 5. And I know that that might look ugly, but you know, in the style point world, that's as good as that guy's going to get. So you're finished. Like, sometimes it just looks like you should be able to do more, but you can't. Are we comfortable about that weird one? Right? That sometimes you have to just be extra careful. This is the next one. I strongly suggest that you get a version of the standard integrals and, you know, put them in a card somewhere, something that will last, because you'll use it a lot, right, over the next 9 weeks or 10 weeks we've got left. You're going to be integrating all the time for different reasons in different contexts, but you're going to be doing it a lot. So you kind of need to know what these guys are. So what is the antiderivative of 3 over 1 plus x squared?
3 times arctan x.
You said the naughty word. You said arctan. Stop saying arctan. It's inverse tan. I'm fighting this one tooth and nail. Arctan is only used by the Americans. Nobody in the world, apart from America in the last couple of 100 years, have ever called anything arctan. It's inverse tan. In fact, the only explanation I can come up for why arctan was ever, created was for printing. It's much easier to type arctan. So you can imagine how old that term must be if it was to do with printing presses weren't very clever at subscripts. But now we've become modern and we use meters and metric system. Oh, wait a minute, America doesn't, right? When you eventually get round to using metric system, maybe at the same time you'll start using inverse tans. Okay? So why don't we start right now? And everybody uses inverses. And when you go to university and you do a math class with your friends and they start saying arctan, will you correct them and say inverse tan? And if you really want to get into trouble, correct your professor instead. You could say something like, excuse me, but I believe arctan is a very archaic way of saying something. Wouldn't it be much more modern to call it inverse tan, right? Be really nose in the air when you do it, right? Agreed? We've got a movement going.
Bonus points for that.
You should, shouldn't you? Right. X equals 1 over root 3, x equals root 3. So now we are going to try and find out what the value of these two guys are. And I'm going to show you a little trick. You are probably going to find that when you deal with the inverse sine, inverse cosine, inverse tangents, that it's a lot more difficult to know what the answer is, because you're used to the unit circle, but trying to find an angle whose tangent is root 3 could require a fair amount of effort. So let me show you a little trick. Go to your calculator and put it in degrees, which breaks every rule I normally do in calculus, because shouldn't calculus always have radians, right? But break the rule for these kinds of questions. Put it back to degrees. Then type in inverse tan of square root of 3. And you see that the answer you get is 60 degrees. So that guy is 60 degrees. And then hopefully you know how to turn degrees into radians and call it that guy. Now, what about the inverse tan of this fella, right? Just this bit, not the whole thing, just this bit. Well, if you go inverse tan of 1 divided by the square root of 3, and do you see that one's 30 degrees? Now, 30 degrees is pi upon 6. Now, wasn't that a lot easier? As long as the angle is a standard angle, this will work fine, right? As long as it's 30, 45, 60, which to be honest is what they will be. Because see, if it was some number like 1 over root 7, you would just leave it like that anyway, right? You couldn't do much more. Now, this guy is worth pi, and this guy's worth a half pi. So the whole answer is a half pi. That's quite a nice answer, isn't it? For what started life as quite an ugly question. Are we comfortable with the shortcut and the whole process? Right. Is there any questions I've done so far that maybe I was too quick and you weren't comfortable with, or you want me to do again or something? Have we been good so far? Looking for nods and things. Right, that'll work for me. Right, next one. Suppose somebody gives you 4 to the power of t. Oh, and I need a number, don't I? Okay. How about from 0 to 1? Because I'm lazy and I don't like big numbers. Okay, antiderivative of 4 to the power of t.
That's going to be 4 to the t over the natural log of 4.
Yep. Then I'll plug in my numbers. 4 to the 1 over log 4. Take away 4 to the 0 over the natural log of 4. Well, that's 4 over the natural, oops, let's try that again. That's 4 over the natural log of 4. Take away 1 over the natural log of 4. Do you see in this case, the two things share a common denominator, so you can combine them into 3 over, whoa, okay, where did that come from? 3 over natural log of 4. And yeah, that's as good as that's going to get, so you're finished. So would you agree 2 to the power of x, 4 to the power of t, z to the power, you know, whatever it is, 6 to the power of z, whatever it is. They're not that bad once you know what the formula for antiderivative is. Everything else is just multiples of that, or variations in that. Now, I'm giving you a chance to redeem yourself. That's all of you who want to use the dreaded arc. What is the antiderivative of that fraction?
Inverse sine.
Okay, so there's 2 on the top, 2 inverse signs. We go with that. 4 on the top, it'd be 4 inverse signs. What would it have been if it'd been -2? Would have been a slight change to the answer. What would this have become if it had been -2 over that square root?
2 inverse cosine.
Now, you plug in the numbers. I'm not going to finish this question, but couldn't we use the calculator trick on these two guys? And then off you go. I think things are going pretty smoothly. You feel comfortable? There's not too many, what on earth is he doing going on? That's the kind of vibe I'm getting. Okay, next question involves us doing a sketch of something and then calculating it. So in this question, it's 28. And the function we've got is this guy. And it's bounded by y equals 0. And then it's bounded by x equals 4. And so I'm going to try and draw a very primitive sketch of what that would look like. Well, I'm pretty sure I know what y equals the square root of x looks like. They say a calculator would be recommended here, but I think you could figure out a square root without doing it in your TI-84. Okay, now x equals 4 is a vertical line about here, right? What does the line y equals 0 look like?
Horizontal line lined up with the origin.
Yeah, so it's basically the x-axis, isn't it? So when you put those three together, do you see what you're being asked to find is the area under this curve? And what do? They give you 4 pictures and you pick the one that looks like that. Right, so that's the first part. Sketch the thing, which I've done, and they give you 4 pictures and one of them looks like that. And then the second one asks you to find this area. Well, isn't the area under this curve the integral from 0 to 4 of the square root of x? Are you happy with that's how you'll find the area? But I don't want to spend a lot of time on this, but wouldn't you call that x to the half and do what you need to do and you get the answer? You're comfortable with how you would calculate that, right? Find x to the half and use a power rule. How about the next one, which is going to be 30. And it's going to be y equals 4 minus x squared and y equals 0. And let's do a sketch of what that would look like. And 4 take away x squared would look like that. And y equals 0 would be the x-axis. So we're being asked to shade that. And there'll be 4 pictures and one of them will look like that. And then you're being asked to calculate what that area would be. So the area under the curve of 4 take away x squared dx. Do you see we got a little bit of problem we didn't have in the first question? I think in the first question, wasn't it pretty obvious it was 0 to 4? Don't I need to know what that start x value is and where to finish, where that x value is? What are those numbers? What's the x coordinate for here and here?
Are you asking us how to find it or what they are?
Just tell me what it is.
Oh, negative
Just
2.
give me the, yeah. How did you find it?
Well, I mean, in order to get 0 out of 4 minus x squared needs to be 4,
Right.
which would be 2.
So what you did is, if I just put it in different words, you found out where 4 minus x squared crossed the x-axis. And you did that by making its y coordinate 0. And you solved 4 minus x squared equals 0. But it was so easy you did in your head. Right. Now, if I put in the numbers -2 to 2, can I just do my ... Is that one pretty easy to integrate and plug in numbers and get 42, whatever it ends up being? Feel comfortable about that, guy? Then we have finished that section. So we're now moving on to our next section. And our next section is kind of not really new, at least the first half. We are going to find indefinite integrals. Indefinite integrals. Right? Sometimes, but very few people do this. They stick the word general in front of it. So indefinite integrals, general indefinite integrals, and you might even, although I think it's highly unlikely, you might even get them called general integrals if somebody's being lazy. I call them indefinite integrals. Indefinite integrals are the ones that don't have numbers, they have plus c. So an example of finding an indefinite integral would be someone solving that. Now, do you notice that there is no limits? There's no 1 to 3 going on here, right? These are left blank. So you're still going to use the power rule, right? Add 1 to the power. And then if you divide by the new power, eventually you get that. So when you do an indefinite integral, aren't you always going to have a plus c tagged on at the end? But aren't you still going to use the same kind of tricks of the trade that we've already been using? Power rules and whatever one it belongs here, and you're going to apply them. So here is an example. This is question 3. And we're going to do the integral of 7x plus a cosine of x. And the indefinite integral then is power rule, add 1 to the power, divide by the new power, and antiderivative of cosine is, yes, it's a positive sign, and then add a c. Can you see that these questions actually have less work to them than the ones that have numbers? And the ones that have numbers are called definite integrals. So if it had the integral from 0 to 2 of this guy, it would be a definite integral that you will be calculating. If they don't have them, because you're going to have a plus c, they're going to be called indefinite integral, right? Similar names, but you know that there's a nuance there, right? They're not exactly the same thing. Oh, how about this fella? What an ugly pair of expressions. There is no way in the world I'm going to be able to find any antiderivatives if I leave them looking like this. Agreed? Now, the 7th root of something is a fractional power, and that fractional power is 1/7. This one is 1 over that guy. What power of x will this be when I write it down? One over the 7th root of x.
X to the power of negative 1/7.
That's all. You know, 1 over x cubed is x to the negative 3, right? 1 over x to the anything is just a negative power. Now, they are ugly, but aren't they also doable? Can't we just use the power rule now? So, you know, I'll try and make sure I don't screw up my fractions. If you add 1 to that, you get 8/7. And if you divide by the new power, you get 7/8. In this one, you add 1 to it, it now turns into positive 6/7. And if you divide by the new power, you get 7/6, and you plus c. There, oh, how am I going to phrase this? Am I finished or can I do better? I know you want me to be finished, but I can do better, right? Tell me the style points. What does it turn into? how do you rewrite x to the power of 8/7 so it looks more like these guys?
Turn it back
With
into a
X.
radical with the 7th root.
And inside? What
X
power
to
of x?
the 8 and then X
Great.
to the 6 on the other one.
Exactly. Now, you might not think that that's an improvement on this, but style points also has a rule, doesn't it, that you should look like the original. Right. So that is a better answer. Oh, I missed that one. I didn't do it in other class. You're getting an example that the other class hasn't seen. At least I don't recollect doing it with them. In fact, I don't think we've ever done decimal powers yet. I mean, we've done x squared and x to the halves and x to the -4s. We've done all those. But I don't think we've done a 1.7 power yet. Do you know it's still the power rule, even though it's downright ugly? Okay. If you do, I'll do this one. If you do the power to this, the rule is add 1 to the power and then divide by the new power. And if you do it to this one, you add 1 to the power and then you divide by the new power. And I'm looking for style points. Is there anything there that could be made even a little bit nicer than it already is?
Fractions.
Which one?
Well, technically both of them. Like,
Yes, but which one? You're right. Technically both of them. But which one kind of does lend itself to reasonably easy conversion?
well, I guess the first one. You just multiply the
No.
top and bottom by 10.
No. I mean, that's what you said
Oh,
is true,
yeah.
Matthew.
Oh yeah, the second one is just 2.
Yeah. So we're going to hit a grey area here. What do I mean by that? Well, I would hope that you would see that. I'm not really too worried, as ugly as that looks, that you fix it. Because can you imagine how horrible some of these decimals would be, you know? And if you tried to fix them, you'd probably end up in a worse place. But if you see something straightforward, I expect you to see that guy. And I would be happy with that. So, okay, I'm breaking my own rule of not making it pretty. And what Matthew said is totally correct. It would be 10 over 27 if you wanted to remove the decimal point and just make it a fraction. And if you did, I'd give you the points because it's right. But if you left it like that, I would leave it.
Quick question for style points. Would you
Mhm.
ever want to like combine the fractions so that they had the same denominator? So let's say times the 2.7 by 5.5 for both of them. So it's all over like 14.85, but it's like combined as one thing. Would that make it better or just way worse?
It would make it a different version of ugly. And if you did that, I would still give you the points. The way I would grade this is when I see that line, I stop looking. And if you do other things, even if you screw up what you do, or the other things look even uglier than the thing I've got, I'm not going to fault you for it because it might have ended up nicer, right? And at least you tried. But if you didn't, I'm okay with that as well. So you're not going to lose points if you think you can do a bit better and it ends up looking worse. I don't think that's an issue because I just kind of say, oh, well, that's right. Well, I'll stop looking. Unless it's really nice answer, and then I'll think, oh, I never noticed that would happen. I wish I'd thought of that. But I wouldn't go back and take points off everybody else because they never saw it either. So, yeah. A totally different example of that question is, can you imagine a question where the answer might end up looking something like this? I guess I'll put a E+1 here and and E. Right? Can you imagine a question that ended up looking like that for whatever reason? Right. Could I combine these two and try and make them a single fraction and do all sorts of other algebra? Sure, I could. I don't think it would be worth it. Would you agree it probably looked worse rather than better when you're finished? Right. So if you got a question like that, I would stop looking. Right. Just call it good. On the other hand, let's be really silly about it. I haven't any idea in the world how that would happen from an integral, but let's suppose it did. I could probably make it happen by weird factors. Do you think that's good? You're happy to leave it as 6/8? No. What are you going to fix it to? Oh God, don't tell me I've...
Three-fourths.
Oh, God in Himmel. Come on, guys. Don't frighten me like that. Were you trying to think of some weird, wonderful thing to do it when it was just a matter of making it pretty? Right? Okay. What about square root of 2 or square root of 4? You're definitely not going to leave it like that. Agreed? Right, we're talking style points, just making it look pretty. What could you do to that fella?
Square root of 4 is just 2.
Okay. Agreed? But what about the square root and the 2 in the top? You can't do anything about it. It's stuck. It's ugly and you can't fix it. Right? You ever heard that saying, you can't fix stupid? Sometimes you can't fix ugly. Some algebraic expressions are just ugly, and there's no algebra out there that's going to make them look any better, right? But if you can fix it, if you can make it pretty, you should try. This is the last question for today. And I choose it because it just looked too simple. Yet sometimes the simple things are the things that screw you up more than the hard things. What do I need to do to get that integral? What do I need to do to get this 8th root of x to the 9?
X to the 9/8.
You happy about that? I am. Remember, if you're trying to get practice, because I know it's a while since you've seen radicals, the 8th root causes the fraction to be 8 on the bottom, and the power of x inside gives you the top power. That's essentially how you convert from radical to fractional powers. Now, it's really ugly looking. It's 17/8. That's what you get when you add 1. You divide by the new power, and then you do your plus c, and then you look for style points. There's not an awful lot you could do, but there is one thing you can do. So what do you do?
Put it back in root form.
Okay. Square root, cube root, 4th root, what kind of root?
8th root of x to the 17th power.
Right. Are these fractional radical guys becoming easier the more you see them? Right, you see the first one and you go, what was that again? And then the second one, okay, but this is about the third one. I think normally by the time you've had the third or fourth one, don't you start just getting used to them? Right. That was going to be the last one, but I can't resist this one because it just popped into my head. What's the antiderivative of that? Oh, it did catch you.
Would it just be pi to the e times x? Like,
It would be.